Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today, for all intents and purposes, we end the first phase of our course. Today we do the fifth and final segment on rational numbers, and it's called dividing rational numbers using decimals. And it reminds me of a kind of a silly story I remember about a little boy in the fifth grade. The teacher asked him, is the noun pants singular or plural? And the kid thought for a while, and he said, well, it's singular on the top and plural on the bottom. By this stage of the course, you're probably so tired of hearing adjectives and nouns and adjective phrases, but if you've stayed with me, I think you've started to see some rewards of this particular system. And today I would like to show you how that leads to an easy way to understand the division of two decimal fractions. So without further ado, let's go to the board and begin today's discussion. I call today's discussion Dividing Decimals, and I begin with a problem which I think all of us know how to do, but I just want to illustrate a point. The first problem says, how much does each person pay if 4 people share the cost of a $23.48 gift equally? Well, basically, if you haven't learned decimals yet, you probably would think of $23.48 as being how many cents? You see, if the decimal point weren't in here, this would look like 2,348. But 2,348 of what denomination? Cents. And how many people are there? 4. So the problem is cents per person. Per means divided by. So we're going to divide 2,348 by 4. If we put 4 into 2,348, and remember the label is cents, and remember when you divide the numbers, so far we leave the noun part alone. The 4 is going to divide the 2,348, and the label, the noun, is going to be cents. So 4 goes into 23 5 times. We subtract 20 from 23, we get 34. 4 goes into 34 8 times with a remainder of 2. We bring down the 8. 4 goes into 28 7 times with no remainder. So the answer is $5.87. Okay, and now if we want to, what can we do? We can change the label from cents to dollars by putting a decimal point over here and putting in the dollar sign. And in fact, if we put the decimal point over here, this is probably the traditional way of handling this. You see, what's interesting is that long before you're taught decimals, you still use them when you're dealing with money. But the important point is that the theory behind this doesn't change even if you're not dealing with money. Let me show you this in terms of a second example. The second example says, how much is 2.324 divided by 7? You see, as soon as I put a third decimal digit in here, somehow you lose the psychological advantage of feeling that you're dealing with money. But it doesn't matter. I'm still going to turn this into a whole number adjective by changing the noun. You see, if the decimal point were left out here, how would I read this? 2,324. But of what denomination? Thousands. You see, the digit furthest to the right is tenths, hundredths, thousandths. So the problem now says, how much is 2,324 thousandths divided by 7? Well, just as in the case with the money problem where I was dealing with cents, I forget about the noun for the time being, and what I do is I divide 7 into 2,324, remembering that the 2,324 is modifying thousandths. So now I just do a regular long division problem, and notice that by leaving out the thousandths here, the division problem I'm doing is purely a whole number division problem. 7 goes into 23 3 times, 21 from 23 is 2, bring down the 2, 7 goes into 22 3 times, 21 from 22 is 1, bring down the 4, 7 goes into 14 twice, and I'm all done with the problem. Well, now, what's the label for this answer? You see, all I did was I divided the 7 into the 2,324. The label here should be thousandths. And how do I indicate the thousandths if I want to use place value? What I do is that thousandths means what? Divide by 1,000. And to divide by 1,000, as we saw in the last module, all we do is move the decimal point 3 places to the left. What decimal point? the one that's assumed to be after the digit furthest to the right. I move that 3 places to the left. That puts the decimal point over here, okay? And also, if I want to leave out the thousands over here, I just move the decimal point 3 places here. And by the way we usually do the problem is to do it in this form at the very beginning. Rather than go through all of this, what we say is, okay, let's divide the 7 into the 2.324 to begin with. What we do is we line up the decimal point to start with. We usually write a 0 over here, if only to remind the person that we do have a decimal point. Then we do the problem exactly the same way as we did it above, only remembering what? That there is now a decimal point over here. If you compare this with this, you'll see that step by step everything is the same, and the answer now comes out to be what? 0.332, 332 thousandths. And if you wanted to check this, in the same way as you would have checked this with whole numbers, all you have to do is do what? Multiply 0.332 by 7. And this is going to check, you see, because without the decimal point, it was 332 thousandths. Oh, what the heck? Why not just do it rather than talk about it? We take 332, multiply that by 7. See, that's 4. 2, carry the 2, 23. Move the decimal point 3 places, and the answer is 2.324. That's what's nice about this course. You will never have to take my word for anything, because as long as it's mathematical, there is an objective way to show if the answer is right. You just do it. All right? Now comes the next wrinkle. At this stage, what you might be saying to me is, you're talking about dividing 2 decimals, and technically, the divisor in both of these cases has been a whole number. What would happen if you had 2 decimals, neither of which was a whole number? And the best way to answer that question is to see what would happen. So problem number 3 says, how much is 0.06 divided by 0.5? See, what makes this problem different from the first 2? In the first 2, the second number, namely the divisor, was a whole number. Where would the decimal point have to go to make this into a whole number? Wouldn't the decimal point, if I moved it over to the right of the 5, make this a whole number? If I move the decimal point 1 place to the right, wouldn't that become a whole number? Sure it would. But what am I doing when I move the decimal point 1 place to the right? I'm multiplying by 10. But we've already seen that in any ratio, if you multiply one number in the ratio by 10, you also have to multiply the other number in the ratio by 10. That's equivalent, as I'll show you later, that when we said what? Given a common fraction, if you multiply numerator and denominator by the same non-zero number, you don't change the rate. At any rate, since I multiply this number by 10, I also have to multiply this number by 10. How do you multiply a decimal by 10? You move the decimal point 1 place to the right. So if I move the decimal point 1 place to the right over here, I now get what? 0.6 divided by 5. That reduces this unfamiliar problem to an equivalent familiar problem. In other words, this problem doesn't look like this problem, but the answer to this problem will be the same as the answer to this problem, because we haven't changed the rate. How do we do this problem now? The same way as we did before. We locate the decimal point. We say 5 goes into 6 once. 1 times 5 is 5. We subtract. The remainder is 1. So what can we do now? Remember, every time we annex a 0, we're not changing anything. I can just keep on tacking on zeros here until such time as I get no remainder. Maybe. Let's just see what happens. I bring down the 0. I say 5 goes into 10 twice. 2 times 5 is 10. I subtract. And what's the answer to this problem? 0.12. Okay? Oh, some people say, well, I don't even like decimals at all. I just hate decimals. I want to avoid them whenever possible. Well, that's going to be terrible if you feel that way. First of all, decimals are a nice place value system. And secondly, at least as the state of the art is right now, anytime you're going to use a calculator, the answer will always come up in decimal form. So you might just as well get used to decimals and coexist with them. But suppose you didn't want to use decimals at all. Let's go back to the beginning of the problem over here and make another observation. If I wanted this to be a whole number, what's the fewest number of places I could move the decimal point here? See, if I moved it 1 place, this was still 0.6. To make this into a whole number, I have to move it 2 places. But to move it 2 places means I multiply by 100. And if I multiply one number in the ratio by 100, I have to multiply the second number in the ratio by 100. So what I could have done was what? Multiply both terms by 100. The 0.06 would then become 6. What happens to 0.5? That becomes 50, because you see, to move the decimal point 2 places to the right, I only have one digit to the right of the decimal point, so I have to annex a 0 as a placeholder. What does that do? It converts that problem into what? 6 divided by 50. That means 6 over 50. Now how does this problem go? 50 goes into 60 once. 50 from 60 is 10. Bring down the 0. 50 goes into 100 twice. 100 from 100 is 0. I get the same answer as before, 0.12. And if you still like to use common fraction notation, some people say, I thought when you have a division, you can always use the first number as the numerator and the second number as the denominator. And the answer is, you have to be careful. See, technically speaking, if I write the problem this way, this technically speaking is not a common fraction. You see, to be a common fraction, both the numerator and the denominator have to be whole numbers. But the important point is, since this is a ratio, whatever properties hold for common fractions still hold here. For example, if you didn't want to have any decimals in here, what could you have done? Simply multiplied numerator and denominator by 100, and what would that have given you? 6 over 50. Another way of doing this problem, if you don't like decimals, is to use the second language. We said that we could always convert from mixed numbers or decimals into the language of common fractions. Remember, 0.06 is what? 6 over 100. And 0.5 is 5 over 10. So written as a common fraction, the problem becomes 6 over 100 divided by 5 over 10. We know how to divide common fractions, namely, leave the first one alone. Okay, made a little mistake over here, but that's why they make erasers at the end of these pens, right? Our fingers. The division sign becomes a time sign. We take the reciprocal, okay? We cancel. And what do we get? 6 times 1 is 6. 10 times 5 is 50. There's the same 6 over 50 that we had when we did the problem the decimal way. Now, in the last lecture, I was showing you the problem of what happens when you deal on a scale of 10, 100, 1,000. And we dealt specifically with the question of, at a rate of 3 out of every 8, how much would you take out of 100? How much would you take out of each 10? How much would you take out of each 1,000? I want to show you that we can do that same thing now, and this is called converting common fractions into decimal fractions. See, we call them decimal fractions because the fraction is being written in decimal form. So suppose the problem said, write 3/8 as a decimal fraction. 3/8 is 3 over 8, so we divide the, see, remember what we do? We swing the 3 down. Obviously, 8 doesn't go into 3, so we make a decimal point, annex a 0, then we say what? 8 goes into 30 3 times. 3 times 8 is 24. 24 from 30 is 6. Well, it didn't stop here. Let's suppose we wanted to stop over here. What does this say? The remainder is 6. So as a mixed number, it's 6/8, which reduces to 3/4. So sometimes the way people will write this is they'll write, in fact, business math books do this all the time. This is a real mongrel notation. You see, look what you have over here. You have a decimal point and a mixed number in the same problem. And all I want you to see is that when people stop over here, read this as if the decimal point weren't in here. Treat the 3/4 as going with the 3. See, so there's only one digit here. And what does this say? You have 3 3/4 of what denomination? Tenths. And by the way, if you want to check this out, 4 times 3 is 12 times 3 is 15. 3 3/4 is 15/4. Tenths means divide by 10. Dividing by 10 puts one more 0 into the denominator. And 15 over 40 breaks down into 3 times 5 over 8 times 5, and that becomes 3/8. So you see, if we stopped at this stage, we get this kind of a mongrel notation, which simply can be read this way, but the problem is what? It's still a non-whole number adjective. Remember we did this in the last lecture? We showed that at a rate of 8, 3 out of every 8, you were taking 3 3/4 out of every 10. See, we can keep on going. We can say, let's go one place further. let's tack on another 0, in which case we proceed the same way as we did before. We bring down the second 0. 8 goes into 67 times. 8 times 7 is 56. We subtract, we get 4. So the fraction part is 4/8. So now we get what? If we wanted to stop over here, we would call this 0.37½. That means what? Forget the decimal point. That's 37½ of what denomination? Hundredths. Now, let's just check this out. 37½. 2 times 37 is 74 plus 1 is 75. That's 75 over 2. Hundredths means to divide by 100. That means annex 2 zeros to the denominator. 75 over 200 is the same as 3 times 25 over 8 times 25. And lo and behold, the problem still checks out. But we still don't have a whole number adjective, so what do? We go on to the next place. We annex one more 0. We keep going the same way as we did before. Now we tack on one more 0. You see, adding on zeros is doing nothing here, because all I'm saying is I'm taking none of the next denomination. I bring down the 0 over here. Now what happens? 8 goes into 40 5 times with no remainder. So now in terms of thousandths, the answer is what? 375 thousandths. And if I want to, I can stop here because I already have my whole number adjective. By the way, I don't have to stop here if I don't want to. I could say, hey, I'm going to bring down another 0. 8 goes into 0 0 times. Remember, every time I bring something down, something else has to come up here. And what does that tell me? How would you read this number? This is 3,750. What denomination? Tenths, hundredths, thousandths, 10,000ths. And you can keep on going this way. Okay? Oh, by the way, another name for 3/8 is what? Multiply numerator and denominator by 2. That would give me 6/16, wouldn't it? I thought this would be a good place to show you one more advantage of decimal fractions. Remember all the time we spent reducing fractions to lowest terms? The beauty about decimal fractions is that if two fractions name the same rate, they will always come out exactly the same as a decimal. So when you're dealing on a calculator, if you divide one number by another and the numbers weren't in lowest terms, you're still going to get the same answer as if they were in lowest terms. Let me show you what I mean here. Let's suppose the problem had said, write 6/16 as a decimal fraction, and suppose you didn't notice that this reduces to 3/8. What would you do? You say 6/16, I'll divide the 16 into the 6. And by the way, you don't have to tack on 1 0 at a time. What you can do is put on a whole bunch of them. And if you don't need all of them, the problem will just come to an end before you get there. And if you need more, you can just tack on more. So look what happens over here. 16 goes into 60 3 times. 3 times 16 is 48. 48 from 60 is 12. Bring down the 0. 16 goes into 127 times. 7 times 16 is 112. I subtract, I get an 8. Bring down the next 0. 16 goes into 85 times. 5 times 16 is 80. 80 from 80 is 0. I can stop the problem right here. And what answer did I get? 0.375. Same answer as I got before. Now, what's interesting is I could give you a lot of experience in converting common fractions to decimal fractions, and we'll do some more of that as the lecture goes on. But what I wanted to really show you here is that in real life, we're frequently called upon to divide two very small decimals. In fact, basically, the whole concept of this advanced subject, which really has its roots in elementary arithmetic, the subject called calculus, deals with looking at an object moving for a short period of time, basically, and measuring how far it went in that short period of time, and from that, projecting how fast it would be moving for a longer period of time. So let me give you a problem that we've dealt with before, but now I'm going to use very small numbers. I say an object travels 0.06 miles in 0.0003 hours. At this rate, how far will it go in 1 hour? In other words, at this rate, what is its speed in miles per hour? You see, we've done problems like this. We've said an object travels 100 miles in 2 hours. What's its average speed? But now you see we're measuring something for what? Over a very, very small time. See, 3/10,000ths of an hour. And in a very small time, the object goes a very small distance. But the theory still remains the same. Miles per hour still means what? Miles divided by hours. How many miles did the object go? 0.06. How many hours did it take? 0.0003. So how do we do this problem? The label is going to be miles per hour, and we're going to take 0.06 and divide that by 0.0003. Now, let's see how to do this problem, and we'll do it in a couple of ways. First of all, we've seen that it's very easy to divide if the divisor is a whole number. How do I make this into a whole number? I've got to move the decimal point 4 places to the right. That means I multiply by 10 to the 4th power. You see, a 1 followed by 4 zeros. I multiply by 10 4 times. If I multiply by 10 4 times over here, I also have to multiply by 10 4 times over here. That means I have to move the decimal point 4 places to the right. After I move it 2 places to the right, I've run out of digits. So therefore, I have to annex 2 more zeros as a placeholder. So this problem now becomes what? 600 divided by 3. But that's a whole number problem. You say, yeah, this is an easy problem. That's 200. But this is a hard problem. Maybe. But what we're saying is that whatever this rate is, it's the same as this. You see, the fact that 200 divided by 3, 600 divided by 3 is 200, says that what? 600 is 200 times bigger than 3. Well, I'm not going to, I'll multiply this out for you in a second, but all I'm saying is, yes, 0.06 may be small, but it's still 200 times bigger than 0.0003. And let's check out to see that this is right. If I take 0.0003 and multiply by 200, 200 times 3 is 600. Then I have what? 4 digits to the right of the decimal point. That means I have to move this decimal point 4 places. After I move it 3 places, I run out of digits. So I put a decimal point in. What's the answer here? 0.0600. These don't mean anything. That's 0.06. So the answer is what? That whatever this rate is, this number here is still 200 times bigger than this. Therefore, what's the answer to this problem? The answer to this problem is that it's 200 miles per hour. You say, my gosh, how could it be that fast? The object only moved 0.06 miles. Yes, but it moved that in what? 3/10,000ths of an hour. And there's lots and lots of 3/10,000ths of an hour in a whole hour. And again, if you want to check this out by translating everything into common fractions, you can do that. You see, 0.06. Let's go back up and make sure you remember how to do this. 0.06 without the decimal point would be a 6. Since there are 2 zeros to the right of the decimal point, that means the denominator is a 1 followed by 2 zeros, which is 100. Without the decimal point over here, all you would see is a 3. So the numerator is a 3. There are 1, 2, 3, 4 digits to the right of the decimal point. So the denominator is going to be a 1 followed by 4 zeros. So when we come back down here, we have what? 6 over 100 divided by 3 over 10,000. How do we handle this? Leave the first number alone, change the division to a times, invert the second number, and multiply. So the 3 goes into the 6 twice, 2 zeros here, cancel with 2 zeros here. 2 times 100 is 200, 1 times 1 is 1, and any number over 1 is itself. 200 divided by 1 is 200, and we have the same 200 miles per hour that way. Now, if everything stayed like this, we could end the lecture right now. We've really done everything that has to be done, except for one small detail. I have worked very hard to pick special divisors that wouldn't cause me a problem. You see, unfortunately, when you're working with denominators which are powers of 10, since the only prime factors of 10 are 2 and 5, whenever you want to take a fractional part of a power of 10, if the number you want to divide 10, the power of 10 into, has a prime factor other than 2 or 5, you're going to wind up with a remainder no matter how many zeros you tack on. And let me show you how that manifests. Suppose I were to say to you, write 5/11ths as a decimal fraction. In other words, let's do the same thing as we did with 3/8. See, with 3/8 we said, okay, we'll divide the 8 into the 3. This way we'll divide the 11 into 5. Now watch what happens over here. 11 goes into 54 times. 4 times 11 is 44. We subtract the 44 from 50, we get 6. We bring down the 0. 11 goes into 65 times. 5 times 11 is 55. The remainder is 5. So by the way, if we elected to stop over here, how would we write this? We would write this as 45. The remainder is 5, so that's 5/11ths. And what denomination? Hundredths And so the way the business math books would do that is they put a decimal point over here. I don't know if that's very clear enough to read. I have a very good hand, but lousy handwriting. We'll do the best we can here. Now you see, we had this problem happen with 3/8 when we had 0.37½, but we said, okay, we'll just keep on going, and eventually this thing will come to an end. Well, you know when we dealt with 3/8, what was the denominator? It was 8. And what does 8 break down into when you write it as a product of primes? It's 2 times 4, and 4 in turn is 2 times 2. The only prime factor of 8 is 2. So we were okay there. Look at the denominator over here. It's 11. That's a prime factor, a prime number itself, and it's neither 2 nor 5. We have to expect a problem here. And watch the problem we run into. Look what happens over here. What will we do next? We say, okay, let's bring down a 0. And we say, okay, 11 goes into 50. 4 times 11 is 44. We subtract, and it's déjà vu. We're back to where we started from. Look what happened here. When we started this problem, we had a 5 followed by endlessly many zeros. When we got down to here, what happened? We had a 5 followed by endlessly many zeros. What's going to happen here is that this thing is going to keep on going forever. It's going to go what? 0.45, 45, 45, 45, 45, 45, 45. Here, kitty, 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 kitty. It's going to keep going 0.45, 45, 45. Not 100 times, not 1,000 times, not 1,000,000 times, not 1,000,000,000 times, but forever. Forever. That's a long time. How's that for a profound statement? Forever is a long time. But this will never come to an end. So how are we going to write it? If this thing never comes to an end, it's going to take us forever to write it. But what happened here is what? The cycle 4-5 keeps repeating over and over again. So what we do is we put a bar over the 45 to indicate that the 45 will repeat forever. In other words, 5/11ths as a decimal is 0.45 with a bar over it, and that means what? 0.45, 45, 45, 45, endlessly. And you're familiar with that. Try to buy one object when they're 3 for $1. You see what's going to happen over here? You say, I'll divide the 3 into 100. There's always a remainder of 1. If you divide into 1,000, there's still a remainder of 1. In other words, when you write 1/3 as a decimal, it's going to be what? 0.33333 endlessly. If you ever stop, it's going to look like what? 0.33333 and 1/3. But since you want to keep writing as a decimal, this thing will never come to an end. You see, and this is kind of an interesting situation over here. And by the way, don't confuse 45 with a bar over it with 45 without the bar over it. You see, if I say write 0.45 as a common fraction in lowest terms, this is a piece of cake. Because basically, what does this say? Without the decimal point, it's 45. But the decimal point tells us it is 45 hundredths. You see, there are 2 digits to the right of the decimal point. 0.45 would be 45 hundredths, which is 45 over 100. 45 is 5 times 9. 100 is 5 times 20. We cancel out the 5s, and we have 9/20ths. See, not 5/11ths, 9/20ths. And how can you tell if this is the right answer? Because if this is right, what should happen? If I take 9/20ths and write it as a decimal, I should get 0.45. Do I? 20 goes into 90 4 times. 4 times 20 is 80. 80 from 90 is 10. Bring down the 0. 10 goes into 105 times. I'm sorry, 20 goes into 105 times. 20 times 5 is 100. There's no remainder. The answer is 0.45. All that says is what? At a rate of 9 out of every 20, you're going to be taking what? 45 out of every 100. And why did that work out so nicely for me? Because 20 breaks down into 4 times 4. 4 breaks down into 2 times 2. And notice that the only prime divisors of 20 are 2s and 5s, so we're okay over here. But notice that 0.45 with a bar over it is 0.454545, and this is just what? 0.45. That means I can keep putting zeros here. Do you notice that as a decimal, the top number is bigger than the bottom one? You see, the way you compare the size of 2 decimals is you look at them term by term. In other words, place by place. And the first place where they're different, whichever one has the bigger digit, is the bigger decimal. In other words, there's a 4 here, a 4 here, a 5 here, a 5 here. So we're tied at the end of 2 innings. Now we go to the next game, a 4 here, a 0 here. That makes this one the bigger one. This one is 5/11ths. This one is 9/20ths. So 5/11ths is bigger than 9/20ths. And by the way, I don't urge that you have to do this, but if you are comfortable with fractions, actually see what the difference is between 5/11ths and 9/20ths. Namely, the common denominator here would be 220. 11 goes into 220 20 times. 20 times 5 is 100. So 5/11ths is the same as 100 over 220. 20 goes into 220 11 times. 11 times 9 is 99. So written with a common denominator, we have 100 over 220 minus 99 over 220, which is 1 part in 220. In other words, these two numbers are not equal, but they only differ by what? 1 part in 220. Can you visualize that in many real-life situations you would say, well, if the only difference is 1 part in 220, I can use these numbers interchangeably. But can you visualize that if you were dealing with billions and billions of items, can you see that an error of 1 part in 220 could be a disaster? If you're off by only 1 mile in 220 miles and you're making a trip to Mars, you're liable to miss the galaxy by the time you get there. That's an interesting possibility. But do you follow the idea here? How big an error is tolerable depends on what kind of a situation we're dealing with. And again, let me remind you of how you measure decimals by size. I'm going to give you just one more problem this way to help you see this. See, which represents the greater number? 0.100324 or 0.099897. See, lots of people see the 9s and the 8s and the 7s and the 1s and the 0s and the 3s, and obviously the sum of the digits of the bottom number is greater than the sum of the digits of the top number. But remember the rule for comparing? You look to see the first column in which there is a different entry. The first difference occurs over here. Which has the bigger entry here? The 1, right? So the top number is bigger. It's like saying that $1 is more than 99 cents. See, this is how you compare the size of fractions. And what that means is, in real life, if you don't want to fool around with 0.45454545 endlessly, what you do is you say, okay, how large an error can I tolerate? And I'll round it off so that the error will be less than the one I'm worried about. So that leads us to our next example, round off 0.454545 endlessly to the nearest millionth. So all you do is you write down 0.45454545. Once you get down to this, you count to the millionth place. You see tenths, hundredths, thousandths, 10,000s, 100,000s, millions. So that's in here. What do you do next? You look to the digit immediately to the right. If that's less than 5, you just drop everything. See, don't bother putting in zeros here, because zeros are the same as nothing, because if there's nothing there, there's none of that denomination. What does this round off to? In other words, to the nearest millionth, 0.454545 endlessly is 0.454545. By the way, what would the next millionth be after 0.454545? See, after 454,545 comes 454,546. So 0.45454545 endlessly is caught where? It's caught between these two numbers, both of which, by the way, happen to be common fraction, happen to be easy to write as common fractions. You see what I'm saying over here? Whenever there are no digits, you can assume that there's zeros. You see, these agree up to here. This is a 4, this is a 0, so 4-5 endlessly is more than this number, but since this is a 6, 4-5 endlessly is less than this number, so I have trapped 0.454545 endlessly between two 6-digit fractions, decimal fractions. And you see, no matter how many digits there are, if there are a billion digits, here's the interesting point here. As long as this thing comes to an end, I can always write it as a common fraction with no trouble at all. Like, take this number over here. I say, write 0.86579431 as a common fraction. Well, without the decimal point, what would I see over here? I would see 86,579,431. So I write that down. Now, how many digits are there to the right of the decimal point? 1, 2, 3, 4, 5, 6, 7, 8. So my denominator is a 1 followed by 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. And there's the answer as a common fraction. And by the way, this can't be reduced. This can't be reduced. How do I know that? Because the only prime factors of the denominator are 2's and 5's, because the denominator is a power of 10. But this number is divisible by neither 2 nor 5, because it ends in a 1. Multiples of 2 end in 0, 2, 4, 6, or 8. Multiples of 5 end in 0 or 5. See, no matter how many digits there are, as long as the thing comes to an end, I can always quickly write this thing as a fraction. The harder part would be, how would you write a decimal as a fraction if it never came to an end? See, this says what? Write 0.45 endlessly as a common fraction in lowest terms. Here's the problem. Suppose I call that n. What does n look like? It's 0.45, 45, 45, 45 endlessly. It never comes to an end. Therefore, there's no place I can come to where I say that this thing here stops. However, if I subtract any number from itself, I get 0. So what I say to myself is, wait a second. If I move the decimal point 2 places to the right, see the repeating cycle is 2 digits? If I move the decimal point 2 places to the right, what number do I wind up with? I wind up with 45.454545. See, what I'm going to do is I'm going to move the decimal point 2 places to the right. And that still gives me what? 45.454545 endlessly. By the way, what do you do when you move a decimal point 2 places to the right? You're multiplying it by 100. So if this was 1n, moving the decimal point 2 places to the right gives me 100 n's. Now watch what happens. If I subtract the bottom from the top, even though this is endless, since the 2 decimal parts are the same, they cancel. But if I subtract the bottom from the top here, I also have to subtract the bottom from the top here. And if I take 1n away from 100 n's, I'm left with 99 n's. So 99 n's must be equal to 45. 99 n's means the 99th multiple of n, that's n times 99. If n times 99 is 45, n must be what? 45 divided by 99, which as a fraction is 45 over 99. 45 is 5 times 9. 99 is 11 times 9. I cancel these. What do I get? 5 elevenths. You see, compare this with problem number 7. I have just done the inverse of number 7. In 7, I started with 5 elevenths and showed that that gives me 0.45 endlessly as a decimal. But in problem 12, I started with 0.45 endlessly and showed that that leads to 7 elevenths. At which point, you may have been one step ahead of me. As I was doing this problem, you may have said, hey, he already gave us the answer to this in problem number 7. So now, let me give you one that we haven't done before, just to see if you can pick up the subtle differences over here. I say if m is 0.123 bar, and what does that mean? It's 0.123, 123, 123 endlessly. I say write m as a common fraction in lowest terms. I do exactly the same thing as I did before. The only difference now is, how does the cycle repeat? It repeats every 3 digits. That means every time I move the decimal point 3 places to the right, I get the same repeating decimal, don't I? But moving the decimal point 3 places to the right multiplies not by 100, but by 1,000. So in other words, if I move the decimal point 3 places to the right, look what happens now. I get 1,000 m's is 123, 123, 123, 123. Look at the decimal parts. They're the same. They cancel out when I subtract, so I'm left with 123. 1 m from 1,000 m's is 999 m's. That's the same as m times 999. That's the same as saying m is 100. See, this says what? What number must you multiply by 999 to get 123? That's called 123 divided by 999. As a common fraction, that's written as 123 over 999. 1 plus 2 plus 3 is 6. That tells me my numerator is divisible by 3. 123 is 3 times 41. 999 is 3 times 333. The 3's cancel, and I'm left with what? 41 over 333, which must be in lowest terms because 41 is a prime number. And again, you don't have to believe me. You may wonder if I'm a suspicious character or not. Why shouldn't you believe me? Wouldn't you rather hear it from me than from a stranger? Why wouldn't you believe me? It's not that you shouldn't believe me. Again, it's that you shouldn't have to. If you don't know if this is right, what do? Just take 41 over 333 and convert that into a decimal and see if you don't get 0.123 endlessly. Look, I'm so confident I'll write the 1, 2, and the 3 in to start with. 333 goes into 410 once. 333 from 410 is 77. I bring down the 0. 333 goes into 770 twice. 666 from 770 is 104. I bring down the 0. 333 goes into 1043 times. That's 999. I subtract. The answer is 41. Now look what happened. When I started this problem, I had a 41 followed by endlessly many zeros. When I got down to here, what did I have? 41 followed by endlessly many zeros. Therefore, this whole cycle is going to repeat. And again, most people say, what am I going to do with 0.123, 123, 123, 123 endlessly? I got other things to do with my life than to just go on endlessly with this thing. And again, all you do is pin the thing down to whatever degree of accuracy you want. In other words, since the first digit here is a 1, that tells you that m has to be more than 0.1, but less than 0.2. In other words, just looking at this digit, you know you're between 1/10 and 2/10. Look at the first two digits. You see a 12, right? So that tells you you're between 12 hundredths and 13 hundredths. Look at the first three digits, 123. So you're between 123 thousandths and 124 thousandths. Do you see how you're pinning this thing down? For example, suppose you come over here. How would you read this number? 123,123. Of what denomination? Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millions. So where is this number? It's more than 123,123 millionths, but less than 123,124 millionths. And now whatever this number is, you've pinned it down so that the error is less than 1 part in a million. And that's what we do in the world of engineering. When we have to make exact measurements, no human measuring instrument is so exact that we can measure more than a certain number of decimal places. So once we're out of the accuracy of our instruments, we round off. That's all there is to it. But you've got to be very, very careful of where you place the bar in this stuff. Let me give you two problems that look almost alike. The first one says, take 0.13 with a bar over it and write that as a common fraction in lowest terms. In other words, if I call that number n, what's 0.13 with a bar over it? It's 0.13, 13, 13, 13, 13. The 13s go on forever, so I move the decimal point 2 places to the right because the repeating cycle is 2 digits. If I move the decimal point 2 places to the right, I get 13.131313, etc. But moving the decimal point 2 places to the right multiplies by 100, so 100 n's are 13.131313. 1 n is 0.131313. If I subtract 1 n from 100 n's, I get 99 n's. If I subtract the bottom from the top, the decimal part drops out. I'm left with 13. If 99 times n is 13, then n must be 13 over 99, and that's in lowest terms because 13 is a prime. So the answer to 14 is 13 over 99. Now watch problem number 15. Problem number 15 looks the same. But if you look at this carefully, look where the bar is. The bar is only over the 3. That tells me that the only thing that's repeating is the 3. See, when I say write 0.13 with a bar only over the 3 as a common fraction in lowest terms, let me call that number p. P is a decimal point, a 1, but the 1 is not part of the repeating cycle. The only part that keeps repeating are the 3's. Now, this is tricky. You see, I don't want the 1 in here because the repeating cycle is the 3's. Where is the first place I can put the decimal point so that all I see is the repeating cycle? I can put it after the 1. But if I put it after the 1, that's multiplying by 10. So if p is 0.13333, etc., 10 p's are 1.3333, etc. Where's the next place I can put a decimal point to have only the repeating cycle? If I moved it one more place, that means 2 places altogether. Wouldn't the repeating cycle just be 0.33333 endlessly? But if I move the decimal point 2 places, I've multiplied p by 100. So 100 p's are 13.3333 endlessly. 10 p's are 1.333 endlessly. Now if I subtract 10 p's from 100 p's are 90 p's. 1.3333 from 13.3333, the 13's cancel. 90 p's is 12. That means p is 12 over 90. 12 is 3 times 4. 90 is 3 times 30. That leaves me 4 over 30. 4 is 2 times 2. 30 is 2 times 15. So the answer is 2/15. And lo and behold, if I check this, 15 goes into 20 once with a remainder of 5. 15 goes into 50 3 times with a remainder of 5. Notice that I started with a 2 followed by zeros, but the first remainder that repeated was a 5. And see, the point I want you to see is that 0.13 bar is not the same as 0.13. In other words, notice in fact that 0.13333 is greater than 0.131313 because they agree in the first two places, but in the third place, this is the greater fraction. I'm not going to bother going through this with you. I just wanted to show you that if you wanted to compare the size of these two in a more familiar form, you could take what? 13 over 99, subtract 2/15. You see, this is your 13 over 99. This is your 2/15. You subtract these. Computations are on the side here. You get 198 minus 195 over 1,485. That's 3 over 1,485, and that reduces to 1 over 495, which says what? These two numbers aren't the same, but how different are they? They differ by 1 part in 495. And you'll have plenty of time to do some experiments this way. But what I wanted to show you is that I can construct decimals which don't have repeating cycles. You see, what did this, first of all, if the decimal comes to an end, it's easy to write it as a common fraction because we just pretend the decimal point isn't there, read the resulting place value numeral, and put it over the appropriate power of 10. If the same cycle repeats endlessly, we can keep shifting the decimal point until we get the repeating cycle to cancel when we subtract. What if the repeating cycle doesn't end? What if there is no repeating cycle? Let me give you an example. See, I say not all decimals represent rational numbers. I'm going to make up a very funny number. I'm going to start with a 28. Then I'm going to add one more 8 to the next cycle. Do you see the idea here? 2 8, then a 2 followed by 2 8s, then a 2 followed by 3 8s, then a 2 followed by 4 8s. And what's going to happen? The next time it's going to be a 2 followed by 5 8s, then a 2 followed by 6 8s. Is this a well-defined decimal? Can you see what I'm doing here? But how can this thing ever repeat the same cycle? Because every cycle has one more 8 than the previous cycle. In other words, I can't use the principle I just used before. Because it's not only doesn't it come to an end, but there isn't even a repeating cycle. And what I'm going to show you for a finale today is that whenever you take a rational number and write it as a decimal, it either has to come to an end or else eventually repeat the same cycle. And the technique for this is known as Dedekin's chest of drawers principle. Isn't that a nice fancy name? This is used in advanced mathematics. And you know what this thing says? It says if you have more objects to put in the drawers than you have drawers to put them in, at least one drawer has to have more than one object. Look, suppose I have a drawer and there's 100 black socks in it and 100 white socks in it. And the room is dark and I can't see. I want to pull out a pair of socks. Well, preferably a matched pair. I reach in. How many socks do I have to pull out before I'm sure I have a matched pair? There are only 2 different colors socks. So by the time I've pulled out 3 socks, 2 of them have to have the same color. Because the worst that can happen is the first 2 times I pull out a white and a black. The third time I have to either pull out a white, which would give me a white pair, or a black that would give me a black pair. Here's a more dramatic example. Suppose you have 13 people in a room. 13 people in a room. Without looking, you can bet that 2 of them celebrate their birthday during the same month. Why is that? Because there are only 12 months in the year. If all 13 people celebrated their birthday in a different month, there would have to be what? 13 months. If there are 400 people in the room, 2 of them have to have their birthday on the same day of the year. Because if 400 people have their birthday on different days, that means there would have to be what? At least 400 days in the year. You say, well, that's great. What does this have to do with fractions? Well, let me give you an example. Suppose my denominator is a 9. It doesn't have to be a 9. It could be 14, 23. I'm just picking 9 as an example. How many remainders are there when you divide by 9? If you're putting books into cartons and the cartons hold 9 books, when you get all through with packing the cartons, what can happen? There are either no books left over, 1 left over, 2 left over, 3 left over, 4, 5, 6, 7, or 8. There are 9 possible remainders, anything from 0 through 8. Therefore, suppose I were to divide 10 different numbers by 9. Since there are only 9 possible remainders, and I have 10 numbers, obviously someplace along the line, 2 of these numbers have to leave the same remainder. I don't know which one it's going to be. Like when I say with 13 people, 2 of them have their birthday in the same month. I'm not saying it's January. I'm not saying it's February. I'm saying they have them during the same month. By the way, could all 13 have their birthday in the same month? It could have happened, but it's still true that at least 2 of them have their birthday in the same month. So the trick over here is going to be what? Suppose I have 2 9ths. I will write 10 zeros after the decimal place. Since there are only 9 possible remainders when I divide by 9, by the time I get to the 10th zero, a remainder has to repeat. It might repeat before that, but it has to repeat. Now let's see what happens over here. 9 goes into 20 twice. 2 times 9 is 18. 18 from 20 is 2. 9 goes into 20 2 times. My, wasn't this nice? In this particular problem, I really lucked out. The second remainder I got was the repeat of the first remainder. It happened right away. Sometimes I won't be that lucky. For example, suppose somebody said to me, oh, by the way, before I go this far, how would we write the answer here? It's a 2 with a bar over it, because the 2 is now going to repeat endlessly. Here's another example. I say write 2 7ths as a decimal. I put down 7 zeros because I know that if a 0 doesn't come up, there are only 6 other possible remainders, so by the 7th decimal place, a remainder either has to repeat or the decimal will terminate. So now what do? I take 2 7ths, I divide the 7 into 2, 7 goes into 20 twice, 14 from 20 is 6, I bring down a 0, oh this is going to be a tough one, 7 goes into 60 8 times, 56 from 60 is 4, I bring down another 0, 7 goes into 40 5 times, 35 from 40 is 5, I got to bring down another 0, 7 goes into 50, 7 times, the remainder is 1. Boy, this is really going on. Bring down another 0, I subtract 7 from 10 is 3. Will this thing ever end? Of course it's going to repeat. There's only 7 possible different remainders I can get. Let's stay patient. I bring down the 0, 7 goes into 30, 4 times, 28 from 30 is 2. Ah, a remainder finally repeated. And since the remainder repeated, the whole cycle is going to repeat. You see, I started the problem with a 2 followed by endlessly many zeros. I finished over here with a 2 followed by endlessly many zeros. Now you see, I went through this kind of fast because there's lots of good material here. There's lots of good material here. And I am somewhat bound by a time constraint. I want you to stay awake. Hopefully still be alive when this lecture is over. So we have to stop someplace. And what I'm hoping is that by my going through this like this, you have seen the most important point. And that is that if you take your time and go one step at a time, dealing with decimals is the same as dealing with whole numbers. And as we get more and more into high technology, decimals become more and more the language of the entire computational community. And as we get more and more into high technology, even people who are not involved in industries that were called computational, little by little are finding out that it is computational. Biology is no longer a subject where you sit down and you classify leaves. Psychology is no longer a subject where all you do is talk about the mind. Economics is no longer the subject where all you do is talk qualitatively about growth. You actually sit down and you measure things. There's statistics, there are all sorts of measurements that require quantification, and these require decimals. But in any event, we have come to a milestone. This completes the lecture part on what we're going to be doing with ratios. For the rest of this course, this is the payoff. We're going to do nothing but applications. And I want you to look forward to that, because if I do my job right and you do your job right, we're going to find out that this is a very exciting and relatively easy subject. And this is the deal I leave you with. In the months that lie ahead, or the weeks or the days, if you give me just a little bit of you, you'll get all of me. But without that little bit of you, I can't give you any of me. I'm going to make this stuff as intuitive as I can so that your bounds in quantification will grow, and so will your upward mobility. Bear with me. Until next time, have fun, study hard, stay young.